Hello. Hello, everyone. My name is Joe Callingham. I'm a Veni Fellow at Leiden University and Astron, the Netherlands Institute for Radio Astronomy. I'm here to give you an introduction to radio interferometry. I've called it a recap of, potentially, because I know you've done Unit 1, 2, and 3 of the DARA course so far. So I'm sure you've been introduced to the basics of radio interferometry before. So hopefully a lot of this stuff I'll present in this lecture will be familiar to you. If anything's not clear, feel free to contact me. I think we'll have a Slack account for the Unit 4 training, which I'll also be contactable over, but also I have my email address here for you. To give you some background, I work on stars and exoplanets in the radio, and also what are called peak spectrum sources, potentially young radio galaxies. Also, I've taught this course, Unit 4 training, twice before, once in Kenya in 2018 and once in Botswana in 2019. So hopefully some of this material will be polished. Anyway, let's get on. So you're a radio astronomer and you want to make lovely images like this. So for people not familiar, this is Fornex A, and you've got these lovely radio lobes hanging out to the right and the left. And it's actually a multi-wavelength image where you can see the optical light in the background, and this is the host galaxy in the center. And we've got this giant black hole that's spewing out jets and producing these lovely radio lobes. So how do we go about making an image like this? And today, the majority of imaging is done using interferometers at radio wavelengths. And we're kind of lucky as radio astronomers. And this is probably one of the reasons why I feel it's reasonably popular as well, is that we sit in a sweet spot in the Earth's atmosphere in terms of what can reach us at the ground. So what I'm showing you here is a plot of essentially atmospheric transparency. You can imagine on the y-axis against wavelength. And so, for example, for wavelengths such as X-ray, for radiation such as X-rays or gamma rays or ultraviolet, this curve is showing that the majority of that is blocked by our atmosphere. So if you try to do X-ray astronomy for the ground, it's just not possible. All the light's mostly absorbed by the time it reaches you, or it's interacted with media on the way. We're very lucky also in the optical range as humans. You can see here where the Roy Gabiv, the rainbow colors, sits right in this perfect window, allowing light to reach the ground. And really, we can see infrared is difficult even to do from the ground as well. It's only once you get to near infrared and submillimeter, this another window begins to open. This is radio waves, and this is where we tend to talk about what type of observing we do. So what is radio astronomy? It's pretty rough, but it's roughly a megahertz, 10 megahertz to a terahertz. So down here, you might have heard instruments called like LOFAR, SK low, operate really low frequencies down here, and then up the higher frequencies, this is telescopes such as ALMA. Okay, so that's why we're lucky that radio waves can penetrate the atmosphere and we can observe them from the ground. So we don't have to spend expensive satellites up. So with radio astronomy, you might notice there's a big difference between the sizes of things. Sometimes you might even have an image ahead of a giant radio telescope compared to, say, a little telescope that our optical colleagues use. Usually the biggest optical telescopes of the current generation are only about 10 meters, and that pales in comparison to the antennae that we use for radio astronomy. And why does size matter? Well, the two most important things for an astronomer should really consider when they're taking observations is what resolution and sensitivity. So resolution, the ability to resolve things. Can you see, for example, a binary star system? You know, if your telescope's not big enough, it might look like a single star. You need to have good enough resolution to be able to resolve those things out. And the other one is sensitivity. A telescope is essentially just a fancy light bucket. What you want to do is sometimes see things very far away or things that are very, very faint, and you just need to collect as much light as you possibly can. And both these things get better as you scale your telescope up. The bigger your telescope goes up, the diameter of your dish or the diameter of your mirror goes up, your resolution goes up, and also your ability to collect more light goes up. And so this is just a very basic equation showing the resolution in theta is directly related to the observing wavelength divided by the diameter of your telescope. So I was just mentioning that your diameter of your telescope is one way of scaling up your resolution, and lambda is your observing frequency. So this is another way of scaling up your resolution. But you can kind of see this is a problem for radio astronomy. And just to give you another background here, this is just a unit of measure of saying how much light you can collect. And A here is your effective collecting area. And so the more sensitive this unit of measure is, it's just a metric. I don't need you to memorize it or anything, but it just means, again, that the better collecting area, the better your sensitivity. Now, to give you a comparison here, this is a cute little cartoon on the left here, but what I'm showing you here is that this is a much bigger telescope than our little optical colleague down here, sitting here, staring at the sky. But let's just give an example. If we just plug away in this equation here, theta equals lambda on d, a 70-meter telescope that's operating at, say, 3 centimeters, the wavelength is 3 centimeters, which is an average observing wavelength for radio astronomy, we only get about 1.5 arc-minute resolution on the sky. Compared to our optical colleague here with a tiny little telescope, a 5 millimeter aperture, so that's just a little lens it's tiny, they get 3 arc-second resolution at 600 nanometers. And that's just because at optical frequencies, your lambda is just so much smaller than it is at higher frequencies. So one way we get around this is by building bigger dishes, right? And you might have even seen this recently in the news. This is Arecibo, or as it once was, unfortunately. Maybe I should change this picture to fast now, but the numbers would have to change. This is one of the largest, or was one of the largest radio telescopes in the world. It's built in a kind of a crater in Costa Rica. And what you've got here is an aperture that is 305 meters wide. So it's huge, right? A giant dish, but it's only got a resolution of about 25 arc seconds when you observe at 10 gigahertz. So it's even worse than that. The human eye, when we look at the sky with our eyes, we've got a resolution of 20 arc seconds, right? You can imagine your eyes are kind of little dishes. Your pupil is the size of the aperture. And so we have about 20 arc second resolution. So even with one of the biggest telescopes in the world, we only get a resolution that's roughly what our eyes can do. So really big is not big enough. So how can we get around this problem? And this is really important for a lot of scientific applications, particularly association between optical sources and radio sources. But I'll wash over that. We just need what we always want as a telescope to do the best science is usually as good resolution and as good a sensitivity as we can get. So is big always better? Well, the answer is, well, why don't we just keep building dishes bigger and bigger and bigger and bigger? Well, you can kind of see the problem here. It becomes a very big engineering problem to make telescopes too big. And this is the famous Green Bank 30-foot telescope in 1988. And this is the next day. It actually collapsed in on itself. So it becomes very difficult to build these large telescopes. But we're lucky. As radio astronomers, we can use some tricks. And one of these tricks, the biggest trick, is interferometry. So there is a better way. And we don't need to just build these bigger telescopes. And this is interferometry to the rescue. So this is a picture of the Very Large Array. This is a famous array in New Mexico in the United States, probably one of the most prolific interferometers of the world. And the trick here is that no longer is our resolution set by the size of our dishes, but it's actually set by what's called the baseline, the distance between the antennas. And so now you can really move these dishes really far apart. And so, for example, the VLA, you can separate these things kilometers, tens of kilometers across, and that kind of simulates, it kind of makes a pseudo dish that's the size of that has a diameter of a kilometer or tens of kilometers. Now, this comes obviously with a lot of caveats, right? There's tricks here. You don't win all the time, right? Otherwise, we just only build interferometers forever. There's a few tricks here, and one of them is just the way you sample the sky. So it's not just like taking a picture with your camera anymore. You have to use what's called Fourier transforms, and trying to understand how you do imagery construction is a little bit more difficult. And I'm going to touch on all these issues today, but obviously this is an introductory lecture. And so hopefully a lot of these topics and ideas I present today will be retouched as the week goes on. So yeah, what I'm saying is we kind of open Pandora's box when we introduce interferometry. One in particular is calibration. I think is harder. People will debate me on this, but like trying to understand how your instrument responds to the sky, you've got a whole bunch of little ones, and they all got slightly different electronics. They all got slightly different pointing issues. They're all their own individual antenna, right? They're not the same antenna, and they've all got their quirks and differences, and so that adds difficulties. You try to make them as uniform as possible. That's why the VLA dishes all looked identical. But there is tricks here, and obviously the EVN, the European VLBI network, which I'm sure you've heard of by now, they're made of all different types of antennas, different sizes, all different backends. Electronics are different, so this makes calibration a little bit more difficult. As I alluded to, and as I'll come to at the end of this lecture, it becomes harder to reconstruct the image. You're not just taking a picture, you're sampling Fourier space, as I'll touch on, and so that means that becomes a lot of issues with that. And this image reconstruction that I'm discussing about is actually an information theory problem. And it means we have too many free parameters to our model. And the last one is an obvious one, is that, okay, we win on resolution by putting all these telescopes apart. I'll just flick back. But you actually don't win on sensitivity necessarily, right? So for example, if I had a telescope that was the size of this entire array, right, kilometers in size, it would collect all the light that could fall on it. Well, I'd try to make sure I'd shape the dish to perfectly focus it all so I could collect all the light. In this case, you can kind of even visualize that obviously light's coming down. Some of it will be collected by, say, this antenna down here, but some of it will just fall in between antennas. And that means you don't get equal sensitivity if you've got a dish the size of your baselines. All right, so let's start introducing how the kind of tricks of interferometry and what's called the geometric delay, and why this is important, and what interferometry is really doing. So we all know light is an electromagnetic wave, and it's oscillating in between electric and magnetic fields. And so this is just a simulation. So at the top left, we got a galaxy far, far away. It's emitting radio light that's being sent down to our antenna. If we just got one, we just collect that light and we try to make an image with it. And you can kind of see, I'm just trying to visualize the oscillation of the wave with these arrows. Now, let's instead imagine we have two antennas, not just one anymore. So we still got our lovely light, but what I'm going to do, and you've probably seen this in physics courses, because I think a lot of your students, a lot of the students listening to this are either physics or engineering students. You can obviously also imagine light as a plane wave, right? So you just got these kind of dotted lines. So this is just light coming in, but obviously each plane wave you can imagine also as like a little photon wiggling towards us, right? But these plane waves just, you can imagine as these light encroaching on us. And what you've got antenna A and antenna B. And you can immediately see that if antenna B is slightly closer to the source A, and we're talking about ever so slightly, because this source is really, really, really far away, right? But we know on the ground, let's just say there's a kilometer between A and B. Obviously, depending where the source is in the sky, that light will ever so slightly arrive just a tiny bit earlier at B than it will arrive at antenna A. And this is called the geometric time delay. And this is just the nature of the fact that where sources are on Earth are going to receive light a tiny nanoseconds difference. But this is really important to understand and correct for, because if we don't know how to exactly time this waves coming in to correct for the geometric delay, or we don't know exactly where our antennas are, we can't use the tricks of interferometry, such as adding up phases and stuff like that. So let's just take away the plane waves for the moment, and we've got these lights coming in, and we've got the geometric delay. And remember, light, as I said, is this oscillating wave. And what's important is, okay, the light's going to arrive at antenna B at a slightly different time than antenna A. But what's also important is, remember, obviously this light left the source, they're going to have the same phase, but now they're going to arrive at different points of the antenna. If we don't correct for the geometric delay, you can see potentially you'll get different types of interference. You'd get constructive or destructive interference. And so you really have to correct for this geometric delay. Oh, sorry, my head's probably in the way of this equation. And it's not a difficult equation, right? You've been doing this type of trigonometry since high school, right? It's just a triangle, and away you go, and you sign. You know what the elevation is. You know how to solve for theta or tau g. You know what the difference is here. This is just a right angle, and then you know what the baseline is. You know the separation, and you know the vector to the source, and you know obviously the light speed of light, c. So this is just a really straightforward thing to correct. But if you don't, you can run into problems of not correctly adding up the light. And this is just an example, right? So you can add sources in phase, you get constructive interference. If you add them out of phase, you get destructive interference. And so the velocity that we've got of the wave here, you can parameterize as a cosine. It doesn't matter. We could have done sine, but cosine's usually more standard, where omega is a frequency and t is the time. And so this is just like a wave equation. And VB stands for voltage. This is just the amplitude of the wave. And once you figure out what the geometric delay is, tau g, parameterized here, obviously you can make sure that you add the light up in the right way, right? You just account for this tiny geometric delay, and then you're going to make sure the correct parts of the wave are going to arrive together. And you can kind of see this green is shifted to what it was before. So remember, these are identical points, but obviously this has to be shifted by those few wavelengths all the way to the end. And that's what that represents here. And this is what this tau g does. So this geometric delay is really a simple thing to solve, but it's just important to note. And this is also why clocks are really important at interferometers. And you might hear about people talking about clock delays. It's because you really need to accurately measure when light arrives at your instruments. But this is standard stuff that's practically done in the back end for yourself. And obviously this geometric delay changes wherever you point on the sky, right? And so if I'm just going to move the source, I want to point at a different source, right? I've done galaxy, I know I've done the Whirlpool galaxy and I've seen it all. I want to go to Cygnus A. I'm going to have to point slightly and the geometric delay will change there too. But again, it's easy enough to solve, but you have to solve it so you add up the waves correctly. Because we'll come to talk about it, is that interferometer is sampling the sky in a very different way than just a single dish. So once you sample these waves, what do you do with it? I don't want to touch on this too much. I think there's a lecture later on it on what's called a correlator. So once you collect these waves, then you send it to a common location, which is called a correlator. And what you do is multiply these waves together and then average them. And this is what this VB is, and then the average of these two things. So what is this all kind of like? Maybe I'm just trying to give you an analogy, just like kind of a side topic. Hopefully this doesn't confuse anyone, but it's kind of like the reverse of the Young's double slit experiment. The physicists in the group have definitely heard of this before. The idea that light acts as a wave, it interferes with itself, right? And so what you have on the left here is plane waves coming in. You have the two slits, and these produce these wavelets, and they interfere at the right-hand side here. Another way to visualize it is like this. And what you end up measuring, what's called fringes, right? And in optical, like for the Michelson-Morley experiment, hopefully people have heard of that before, you're actually measuring, the intensity of light. The trick with radio astronomy is that we can store phase, and that's why we multiply in the correlator as well. So that allows us a lot more versatility. And so for a radio, you can kind of already see what happens here is that these slits are our antennas now. And what we're doing is measuring this interference pattern, or these fringes is another phrase for these words. I know this is a little jargon, introductory lecture, I'm sorry, but I just hopefully once you get used to these terms, it will become subconscious, and these will and you'll have a grapple for other lectures that will come. So you have these fringes, and what you can do with a radio interferometer is take this pattern and then reconstruct what the source looks like over here. So really what you're measuring with an interferometer is this kind of weird fringe pattern, but somehow using the tricks and a little bit of black magic, as I'll touch on a bit of this lecture, you're able to take this pattern, which is a Fourier transform of the sky or the source, and backtrack it. And then that's what I mean by the word reconstruct what the image was at the start. So this multiplying interferometer, the way to visualize it, you can see, remember I talked to you about this average, and these are these cosine terms I introduced just earlier. And what you end up being with, obviously, when you average with this cosine term, you're just left with the geometric delay term here too. And this R is just this is just our fringe pattern, and this general, so just like what I showed before with the Young double slit experiment, these are fringes. And what you're seeing here is the general primary beam. So this is just your field of view, more or less, influences this general envelope. And the spacings here are influenced by your baselines, the length of your baselines. And this is what these equations are showing at the bottom here. Your primary beam envelope is at some point the size of your instrument and the wavelength you're observing, and the fringe is the size of the wavelength you're observing and the baseline. And this is just r theta, and theta being an angle on the sky. Now, before I go further, I'm going to introduce a lot of Fourier transforms. Now, I have the assumption that everyone has been introduced to Fourier transforms. There's this marvelous trick, which is kind of amazing, by a French mathematician that realized that you can pretty much approximate any shape, or you can exactly approximate with infinite amount of terms, any shape with the sum of sinusoidals. And when you have when you have difficult patterns such as this square wave, you need a whole bunch of sinusoids to do it. And you can kind of see you don't quite perfectly reconstruct it. But the idea behind the Fourier transform is if I give you infinite amount of sinusoids, I can perfectly reconstruct this reference signal. And so it's a mathematical tool that decomposes a signal into its sinusoidal components. And it contains all the information, which is amazing, right? So I can take a Fourier transform and go back and forth as many times as I like, as long as I don't lose information, and as long as I don't do any silly errors or maybe like any computational issues, I can recover all this information perfectly. And so that's the trick with the interferometer. Remember, I told you, and I showed you with the Young double slit experiment, is essentially what you're doing is taking a Fourier transform of the sky with an interferometer, right? The antennas are those slits. And so what's happened is that what we're recording through those fringes and all that kind of stuff is a Fourier transform of our source. And what we need to do is go back. So you can kind of imagine this problem. We start on the right and we actually want to go to our reference signal on the left. And this will be definitely covered in a lot of depth in your imaging lectures. But again, these are just kind of introducing the concepts. Hopefully I'm not going too quick, but I will be online for any questions. So this is an example of measuring the sky, kind of already what I mentioned. So we just got brightness of the sky. Just imagine it's maybe a chunk of the Milky Way or something like that. And we've just got it. It varies as a position of the sky theta, right? So just imagine, you've probably looked up in the night sky with your eyes. Hopefully you have, outside of a big city, and you can see this big band of the Milky Way, but it's got different structure. And that's what I'm trying to show here with this plot, is depending where exactly on the sky you are, theta, you're going to have a slightly different response. And the interferometer is going to measure that, and it's going to sample this kind of function with different baselines, but that sampling can be decomposed into sine and cosines. And so this is what's called a visibility. In reality, it's a 2D response, but I'm just showing the 1D for simplicity here. And what I'm trying to show is that when you take a sample of the sky, what you've got is these terms such as the amplitude of your signal, but also these phase components, depending where the source is exactly in the sky. An important thing to note is the sky brightness distribution is not an even function. So to recover what these visibilities that are got the amplitude and the phase of the light and all this kind of stuff, that's our ultimate measurable in radio astronomy, you need both sine and cosines to recover this, because it's not an even function. If it was an even function, we just do cos and we go away with it, but because it's an odd function, we need both. So this comes to a very famous function that is used in radio astronomy. You don't need to understand the absolute elements of this. I'm just introducing it as a concept, and it's called the Van Sittert-Zernike function. And this is now where I've got the 2D components. And what it's showing is that the coherence function of the radio field in space is a Fourier transform of the brightness distribution of the source. So what I'm trying to say is that when you measure with a radio telescope, what you see on the sky, with a radio interferometer, what you end up getting out is a Fourier transform of that. And these U's and V's in this, and you can kind of see this is just a Fourier transform of your visibilities. What you're seeing here is amplitude, but you've also got, it's obviously a complex number. This is what this minus 2 pi I is. And you've got these other two components where theta and phi are positions on the sky, because it's 2D, right? Sky is not just those one line anymore. It depends where you point. That's what phi is parameterizing here. And what you've got is these UV coordinates. And this is actual location on the sky, x1 minus x2 and y1 minus y2. And this is what we call the UV plane. It's a way of thinking about your sampling of the sky using a radio interferometer before you take an image. If we change our citations slightly, such as we rewrite the voltages in terms of the complex number, we can rewrite this a little bit nicer and elegantly. It's just the sum of these components, where the U and V is now in the cosine, and you don't have to worry about the exponentials anymore, which is obvious. This is just Euler's formula. So to visualize this, our Fourier components in this UV plane every single time you sample with a radio telescope, you get one of these measurements in the UV plane, and that allows you to reconstruct it. I think this is reasonably complex. I would touch on this again in imaging. This might be a little bit complicated right now. So I feel like it's better to do with an example, and then hopefully later in the lectures, this will be a little bit easier. So let's start with a cat. Oh, sorry, this is some text in the background. So this is not my cat. This is Anna Scaife's work. She did a great work. So what we're going to do is we're going to imagine this is a picture of our cat, right? Well, it is a picture of a cat. I don't need you to imagine it. It's a picture right there. But what I'm trying to say is that we're going to play around with some Fourier transforms to see how sampling impacts what you see and how you can reconstruct images. Now, the trick with is obviously we've taken a photo, right? So we've taken a photo. That means we used a full aperture on our phone, for example, and we sampled all the Fourier components because it's just a single component. It's not an interferometer, right? But we can take a Fourier transform. So remember, I told you, with an interferometer, we're going back to forth here. So really, when we sample, if we just had an interferometer and we tried to sample the cat, what we'd get out, what we'd measure after the correlator would be this function on the right. And this is our UV plane here, right? So you've got U on the bottom, V on the V on the y-axis, U on the x-axis. And this is just telling you, well, one, does the right look like your cat at all? No, it doesn't. Our brains don't work in Fourier space very well. There's a few radio astronomers that work in Fourier space, and I bow down to them. They're very, very, very intelligent in the way they can do that, but I don't work in Fourier space. So you imagine this is our radio telescope, and we are a priori, like we don't know what our left looks like. We have to go from this plane on the right back to this plane on the left. And that's what you'll learn in your imaging capabilities as well. But just to give you some idea of like what we're doing and how sampling things differently is really, I think, a good way to recover this stuff right now. So anyway, so this is our cat on the left. This is our Fourier cat on the right. And what I wanted to say is that when you sample with an interferometer on the right here, our UV plane is completely filled on the right. That's because you've sampled all the Fourier components of the cat. But with the interferometer, remember, there's these gaps, right? And you'll learn there's different ways of closing these gaps, but you always will have a gap. That's the nature of an interferometer, right? You've got different telescopes and you're measuring visibilities on baselines. And so what that means is that you won't have a filled plane, because we could go back and forth as much as we like right now, because we have all the information in the Fourier space. We have all the information in image space, the picture of our cat. But what I'm going to do now is carve out a little bit of information. I'm going to delete it, and then I'm going to ask if I can recover the image. And so what I'm going to do, you can see this red box. I'm going to delete everything outside the red box and then do the inverse Fourier transform. Oh, sorry. I'm going to delete everything inside the red box and do the inverse Fourier transform. So now I have no information on the inside. And what's happened here is the thing we remember with Fourier transforms, which is a little bit counterintuitive because you're doing this coordinate transform, things on short scales, so things within the box, recover the large scale structure, while vice versa, things on the large scale that are far out in the UV plane recover the short, recover the long scale structure. Things on the inside sensitive, the tiny things are sensitive to the largest things on the sky. So the small Fourier components are sensitive to the largest components in the sky, while things far out are sensitive to the smallest components. And so what's happened here, it's applying what's essentially called a high pass filter. What you've got here is I've reconstructed the cat, but we've only got the really sharp features left, right? So you can kind of see the cat, you can see the eyes, you can see the whiskers, the edge of the ears really defined, but you kind of lost the structure in the middle of the cat. And we can do the reverse, right? Imagine I only keep the middle and I throw away the outside. Obviously, you can see the resolution's gone down. We don't have that sharp features anymore, but you've recovered more of, like, say, the diffuse structure of the cat. So just to kind of take away, small Fourier frequencies equal large scale image structure. Large Fourier frequencies equals small scale structure. So big is small and small is big. So that's been a whirlwind tour of interferometry and some of the details. Just a few things that I just want to recap before I finish. One, the key to interferometry is a geometric delay. You have to account for this. But in reality, with modern instruments, this is all done in the back end, and it's because we know it very, very well now. The other thing to take away is the sky is not symmetric. We need both cosine and sine waves to make a picture of it. And interferometers measure what are called the complex visibilities. And these are just the Fourier components of the sky. And so that means you're getting a Fourier transform in. And so to get the image, that beautiful image I showed you of the radio galaxy at the start, you need to do an inverse Fourier transform. You need to go back, just like our cat, right? So instead of getting our cat, we've got some Fourier components, some junk in the UV plane. And what we need to go is back to the image plane. We just need to rewind it. So I just have to thank Anna Scapes, Ron Eakers, and John McKean, where I've recycled a few of their lectures and material there with addition to my own. And as I said, I'm happy to take any questions, and I hope that was reasonably clear. And I hope you enjoy the rest of your training. Thanks.